Big data architecture. Here you can see a big data architectural style. So this is the architectural diagram for big data architecture style. A big data architecture is designed to handle the data ingestion, processing and analysis of data that is too large or complex for traditional database systems. Now we are focusing on data sources. All big data solutions start with one or more data sources. Here you can see data sources of big data. Here you can see social network data like from Facebook. Here you can see financial data, for example, PayPal. Here you can see multimedia data, for example, Netflix. Data from ERP system, for example, SAP. Here you can see Internet of Things, and here you can see mobile apps data, for example, Uber. Here you can see major data sources for big data strategy. Operational and analytical database data stored in NoSQL, SQL and Hadoop. Text here. Multimedia files, digital files, pictures and videos. Text here. Internal documents, data from files created by word processor and HTML pages. Text here. Archived data, scanned versions of statements and forms. Text here. Machine log data, data from machine level like activity on the server. Text here. Social media data, unstructured text from social media platform. Text here. Sensor data, data from sensors attached to smart devices. Text here. Public web sources, public data from private or government sources. Text here. As an example, we can consider application data stores such as relational databases. Relational database, a database in which all data are represented in tabular form. The description of a particular entity is provided by a set of its attribute values stored as one row or record of the table called a tuple. Similar items from different records can appear in a table column. The relational approach supports queries that involve several tables by providing automatic links across tables. Payroll data, for example, can be stored in one table and personal benefit data in another. Complete information on an employee can be obtained by joining the tables on employee identification number. In more powerful relational data models, entries can be programs, text, unstructured data in the form of binary large objects, blobs, or any other format the user requires. The relational approach is currently the most popular model for database management systems. As another example, we can consider static files produced by applications such as web server log files. Web server log is a log file or several files automatically created and maintained by a web server consisting of a list of activities it performed. As another example, we can consider real-time data sources such as IoT devices. IoT devices are part of the large concept of home automation, which can include lighting, heating and air conditioning, media and security systems, and camera systems. Long-term benefits could include energy savings by automatically ensuring lights and electronics are turned off, or by making the resident in the home aware of usage. Now we are focusing on data storage. Data for batch processing operations is typically stored in a distributed file store that can hold high volumes of large files in various formats. This kind of store is often called a data lake. Here you can see big data storage technologies and CAP theorem. We present the categorization based on the two pairs given by Brewer for modern distributed system to show their success and capability towards Brewer's theorem. Intersection of two features presents the criteria. For example, consistency partition resilience and availability partition resilience. Recent distributed systems for storing big data satisfy either pair. Consistency and partition resilience are presented in this figure and as CP, and the intersection shows the list of technologies that possesses these two features from each data model. The pair availability partition resilience is also shown in this figure, and at the intersection like Cassandra, Voldemort and DynamoDB. We previously explained that according to Brewer, it is not possible for a system to fully support consistency and availability at the same time. Therefore, for a distributed system, it is important to satisfy either choice, but partition resilience is mandatory. Here, with related to consistency, CP, we can include key value, Scalaris, Redis, Memcache DB, Berkeley DB, column oriented, HBase, Hypertable, Bigtable, document, MongoDB, Terrastore, Rethink DB, graph, Hypergraph DB, Neo4j, Elego graph, Infinite graph. With related to availability, AP, key value, Aerospike, Voldemort, KAI, Risk, DynamoDB, column oriented, Cassandra, document, SimpleDB, CouchDB, OrientDB, Rocket U2, Quix, graph. Uh, as an example, we can consider Azure Data Lake Store. Users can store structured, semi-structured or unstructured data produced from applications including social networks, relational data, sensors, videos, web apps, mobile or desktop devices. A single Azure Data Lake Store account can store trillions of files, where a single file can be greater than a petabyte in size. As another example, we can consider blob containers in Azure storage. A container organizes a set of blobs similar to a directory in a file system. A storage account can include an unlimited number of containers, and a container can store an unlimited number of blobs. We are now focusing on batch processing. Because the data sets are so large, often a big data solution must process data files using long-running batch jobs to filter, aggregate, and otherwise prepare the data for analysis. Usually, these jobs involve reading data source files, processing them, and writing the output to new files. Here you can see Lambda architecture building blocks for AWS. Each layers in the Lambda architecture can be built using various analytics, streaming, and storage services available on AWS platform. The batch layer consists of the landing Amazon S3 bucket for storing all the data, example clickstream, server, device logs, and so on, that is dispatched from the one or more data sources. The raw data in the landing bucket can be extracted and transformed into batch view through for analytics using AWS Glue, a fully managed ETL service on AWS platform. Data analysis is performed using services like Amazon Athena, an interactive query service, or manage Hadoop framework. Using EMR. Using Amazon QuickSight, customers can also perform visualizations and one-time analysis. Finally, the serving layer can be implemented with Spark SQL on Amazon EMR to process the data in Amazon S3 bucket. From the batch layer. The merged data set can be written to Amazon S3 for further visualization. The metadata, for example, table definition and schema associated with the processed data, is stored in the AWS Glue catalog to make the data in the batch view immediately available for queries by downstream analytic services in the batch layer. The data ingestion step comprises data ingestion by both speed and batch layer, usually in parallel. For batch layer, historical data can be ingested by any desired interval. For batch ingestions, customers can use AWS Glue or AWS database migration service to read from data from source systems such as RDBMS, data warehouse, and NoSQL databases. Data transformation is a key step in Lambda architecture where the data is manipulated to suit downstream analysis. The raw data is ingested into the system in the previous step is usually not conducive to to analytics as is. Transformation step involves data cleansing that includes deduplication, incomplete data management, and attribute standardization. It also involves changing the data structures if necessary, usually into an OLAP model to facilitate easy querying of data. Amazon Glue, Amazon EMR, and Amazon S3 form the set of services that allow users to transform their data. Let's dive deeper into the data transformation and look at the various steps involved. The data ingested via the batch mechanism is put into an S3 staging location. This is a true copy of the source with little to no transformation. The AWS Glue data catalog is updated with metadata of new files. Glue data catalog can integrate with Amazon Athena, Amazon EMR, and forms a central metadata repository for the data. An AWS Glue job is used to transform data and store it into a new S3 location for integration with real-time data. AWS Glue provide many CAN transformation, but if you need to write your own transformation logic, AW2 Glue also support custom scripts. Users can easily query data on Amazon S3 using Amazon Athena. This helps in making sure there are no unwanted data elements that get into the downstream bucket. Getting a view of source data upfront allows development of more targeted metrics. Designing analytical applications without a view of source data or getting a very late view into the source data could be risky. Since Amazon Athena uses a schema on read approach instead of a schema on write, it allows users to query data as is and eliminates the risk. Amazon Athena integrates with Amazon QuickSight, which allows users to build reports and dashboards on the data. By following the preceding steps, you can create a scalable data transformation platform on AWS. It also important to note the Amazon Glue, Amazon S3, Amazon Athena are serverless services. By using these services in the transformation step, of the Lambda architecture, we can remove the overhead of maintaining servers and scaling them when the volume of data to transform increases. Now we are focusing on data analysis. In this case, you apply your query to analyze data in the 3 layers. Batch layer, the data source for batch analytics could be the raw master dataset directly or aggregated batch view from the serving layer. The focus of this layer is to increase accuracy of data analysis by querying the comprehensive dataset across multiple all dimensions and all available data sources. Serving layer. In this layer, the merge query is aimed at joining and analyzing the data from both the batch view from the batch layer and the incremental stream view from speed layer. This suggested architecture on the AWS platform includes Amazon Athena for the batch layer. For serving layer, we recommend using Spark SQL on Amazon EMR cluster to consume data from S3 in the batch layer. The final step in Lambda architecture workflow is metrics visualization. The visualization layer received data from the batch stream and combined serving layer. Purpose of this layer is to provide a unified view of the analysis matrices that were derived from data analysis step. Batch layer, the output of the analysis metrics in the batch layer is generated by Amazon Athena. Amazon QuickSight integrate with Amazon Athena to generate dashboards that can be used for visualizations. Customers also have a choice of using any other BI tool that supports JDBC or DBC connectivity. These tools can be connected to Amazon Athena to visualize batch layer metrics. Serving layer, the combined dataset for batch and stream matrices are stored in a serving layer in the S3 bucket. This unified view of the data is available customers to download or connect to a reporting tool like Amazon QuickSight to create dashboards. Security. As part of AWS shared responsibility model, we recommend customers use the AWS security best practices and features to build a high secure platform to run Lambda architecture on AWS. There are some points to keep in mind with this security perspective. Encrypt end-to-end. Architecture proposed here make use of services that support encryption. Make use of native encryption features of the service wherever possible. Server-side encryption (SSE) is the least disruptive way to encrypt your data on AWS and allows you to integrate encryption features into your existing workflows without a lot of code changes. Follow the rule of minimal access when working with policies. Identify and access management IAM policies can made very granular to allow customers to create restrictive resource level policies. This concept is also extended to S3 bucket policies. Moreover, customers can use S3 object level tags to allow and or deny actions at the object level. Make use of these capabilities to ensure that resources in AWS are used securely. When working with AWS services, make use of IAM role instead of embedding AWS credentials. Have an optimal networking architecture in place by carefully considering the security groups, access control list, ACL, and routing tables that exist in the Amazon Virtual Private Cloud, Amazon VPC. Resources that do not need access to the internet should not be in the public subnet. Resources that require only outbound internet access should make use of the network address translation NAT gateway to allow outbound traffic. Communication to Amazon S3 from within the Amazon VPC should make use of the VPC endpoint for Amazon S3 or AWS private link. Here you can see 3 layers: batch layer, merge serving layer, speed layer. Data source is connected to landing S3 bucket. It will connect it to batch under batch processing to AWS glue crawler. It is connected to AWS glue catalog. It is connected to Amazon Athena. It is connected to visualization. AWS glue catalog also connected to Amazon EMR. Then it is connected to merge view S3 bucket. It is connected to visualization. Landing S3 bucket also connected to AWS glue ETL, and AWS glue crawler also connected to batch view S3 bucket. Amazon glue ETL also connected to batch view S3 bucket. It is connected to Amazon EMR. It is connected to merge view S3 bucket. It is connected to visualization. As an example, we can consider running SQL jobs in Azure Data Lake Analytics. Using Data Lake Analytics, users can develop and run parallel data transformation and processing programs in USQL, a query language that combines SQL with C#. USQL was designed as an evolution of the declarative SQL language with native extensibility through the user code written in C#. USQL uses C# data types and C# expression language. As another example, we can consider using Hive, Pig, or custom MapReduce jobs in an HD inside Hadoop cluster. Apache Hive is a data warehouse software project built on top of Apache Hadoop for providing data query and analysis. Hive gives an SQL-like interface to query data stored in various databases and file systems that integrate with Hadoop. Traditional SQL queries must be implemented in the MapReduce Java API to execute SQL applications and queries over distributed data. Hive provides the necessary SQL abstraction to integrate SQL-like queries, HiveQL, into the underlying Java without the need to implement queries in the low-level Java API. Since most data warehousing applications work with SQL-based querying languages, Hive aids portability of SQL-based application to Hadoop. While initially developed by Facebook, Apache Hive is used and developed by other companies such as Netflix and Financial Industry Regulatory Authority (FINRA). Amazon maintains a software fork of Apache Hive included in Amazon Elastic MapReduce on Amazon Web Services. Apache Pig is a high-level platform for creating programs that run on Apache Hadoop. The language for this platform is called Pig Latin. Pig can execute its Hadoop jobs in MapReduce, Apache Test, and Apache Spark. Pig Latin abstracts the programming from the Java MapReduce idiom into a notation which makes MapReduce programming high level, similar to that of SQL for relational database management systems. Pig Latin can be extended using user-defined functions (UDFs), which the user can write in Java, Python, JavaScript, Ruby, or Groovy, and then call directly from languages. MapReduce is a programming model and an associated implementation for processing and generating big data sets with a parallel distributed algorithm on a cluster. As another example, we can consider using Java, Scala, or Python programs in an HD Insight Spark cluster. Java is a high-level class-based object-oriented programming language that is designed to have as few implementation dependencies as possible. It is a general-purpose programming language intended to let programmers write once, run anywhere. WORA, meaning that compiled Java code can run on all platforms that support Java without the need for recompilation. Java applications are typically compiled to bytecode that can run on any Java virtual machine (JVM), regardless of an underlying computer architecture. The syntax of Java is similar to C and C++, but has a fewer low-level facilities than either of them. Java runtime provides dynamic capabilities such as reflection and runtime code modification that are typically not available in traditional compiled languages. As of 2019, Java was one of the most popular programming languages in use according to GIT Hub, particularly for client-server web applications with a reported 9 million developers. Scala is a strong statistically typed general-purpose programming language which supports both object-oriented programming and functional programming. Designed to be concise, many of Scala design decisions are aimed to address criticism of Java. Python is an interpreted high-level general-purpose programming language. Its design philosophy emphasizes code readability with its use of significant indentation. Its language constructs, as well as its object-oriented approach, aim to help programmers write clear, logical code for small and large-scale projects. Real-time message ingestion. If the solution includes real-time sources, the architecture must include a way to capture and store real-time messages for stream processing. This might be a simple data store where incoming messages are dropped into a folder for processing. However, many solutions need the message ingestion store to act as a buffer for messages and to support scale-out processing, reliable delivery, and other message queuing semantics. Here you can see how Gigabit uses Absolver on AWS. Absolver, an APN advanced technology partner and data analytics competency partner, focuses on helping companies that generate event streaming quickly analyze data using Amazon Simple Storage Service, Amazon S3, through its easy-to-use, highly scalable platform and visual tool. Absolver enables companies to drive value from both real-time and historical data by securely combining the data through its platform. It took only a few hours of discussion and experimentation for Gigabit to realize the value it could drive by using Absolver in AWS. Using Absolver stream processing platform, Gigabit built a working proof of concept for its real-time pipeline in hours. Today, Gigabit uses Absolver extensively and continues to scale its use of platform each quarter. Absolver integrates Gigabit's Amazon S3, Amazon Athena, Amazon Elastic MapReduce, Amazon EMR, and Amazon Kinesis Firehouse footprint. Using Kinesis Firehouse, the company injects multiple data streams into its Amazon S3 data lake. It then uses Absolver for ETL extract, transform, load to build complete user profiles in real time. Company also uses Absolver and Athena for business intelligence BI reporting that is used by its data science team to improve machine learning models. Here you can see a Gigabit server. It is connected to Amazon Kinesis Firehouse. It is connected to S3 bucket. It is connected to Amazon EMR. It is connected to Spark. S3 bucket also interact with Absolver data processing through clean and enrich, join multiple streams, prepare device profiles. Absolver is connected to Absolver data processing is connected to Absolver data serving through device profiles, and it is connected to real-time decision engine. Absolver data processing is also connected to Amazon Athena through Parquet files, and it is connected to data science. As an example, we can consider Azure Event Hubs. Azure Event Hubs is a big data streaming platform and event ingestion service. It can receive and process millions of events per second. Data sent to an event hub can be transformed and stored by using any real-time analytics provider or batching storage adapters. Azure IoT Hubs. IoT Hub is a managed service hosted in the cloud that acts as a central message hub for communication between IoT application and its attached devices. You can connect millions of devices and their back-end solutions reliably and securely. Almost any device can be connected to an IoT hub. As another example, we can consider Kafka. Apache Kafka is a framework implementation of a software bus using stream processing. It is an open source software platform developed by the Apache Software Foundation, written in Scala and Java. The project aims to provide unified high throughput, low latency platform for handling real-time data feeds. Kafka can connect to external systems for data import export via Kafka Connect and provide Kafka streams, a Java stream processing library. Kafka uses a binary TCP-based protocol that is optimized for efficiency and relies on a message set abstraction that naturally groups messages together to reduce the overhead of a network round trip. This leads to large network packets larger sequential disk operations, contiguous memory blocks, which allow Kafka to run burst stream of random message writes into linear writes. Now we are focusing on stream processing. After capturing real-time messages, the solution must process them by filtering, aggregating, and otherwise preparing the data for analysis. The processed stream data is then written to an output sink. Azure Stream Analytics provides the managed stream processing service based on particularly running SQL queries that operate on unbounded streams. Here you can see Lambda architecture building blocks on AWS. The speed layer can be built by using following three options available with Amazon Kinesis. Kinesis data streams and Kinesis client library. Data from the data source can be continuously captured and streamed in near real time using Kinesis data streams. With Kinesis client library, you can build your own applications that can pre-process the stream data as they arrive and emit the data for generating incremental views and downstream analysis. Kinesis data firehouse. As data is ingested in real time, customers can use Kinesis data firehouse to easily batch and compress data to generate incremental views. Kinetic data files also allow customers to execute their custom transformation logic using AWS Lambda. Before delivering the incremental view to Amazon S3. Kinesis data analytics. This service provides the easiest way to process the data that is streaming through Kinesis data stream. Or Kinesis data firehouse using SQL. This enables customers to gain actionable insight in near real time from the incremental stream before storing it in Amazon S3. Finally, the serving layer can be implemented with Spark streaming on Amazon EMR cluster, which consumes data directly from Amazon Kinesis stream to create a view of the entire data set, which can be aggregated, merged, and joined. Merged data set can be written to Amazon S3 for further visualization. Both of these components are part of the same code base, which can be invoked as required, thus reducing the overhead of maintaining multiple code bases. Data ingestion. Data ingestion step comprises data ingestion by both the speed and batch layer, usually in parallel. For the speed layer, The fast moving data must be captured as it is produced and streamed for analysis. The data is immutable, time triggered, or time ordered. Some examples of high velocity data include log collection, website clickstream logging, social media stream, and IoT device event data. This fast data is captured and ingested as part of the speed layer using Amazon Kinesis data streams, which is the recommended service to ingest streaming data into AWS. Kinesis offers key capabilities to cost effectively process and durably store streaming data at any scale. Customers can use Amazon Kinesis Agent, a pre-built application to collect and send data on Amazon Kinesis stream. Or use Amazon Kinesis producer library KPL as part of custom application. The Kinesis analytics enable users to get a view into their data stream in real time, which makes downstream integration to batch data easily. With related to data transformation, for the real-time ingestions, data transformation is applied to on a window of data as it passes through stream and analyzed iteratively as it comes into stream. Kinesis data streams, Kinesis data firehouse, and Kinesis data analytics allow you to ingest, analyze, and dump real-time data into storage platforms like Amazon S3 for integration with batch data. Kinesis data streams interfaces with the Spark streaming, which is run on an Amazon EMR cluster for further manipulation. Kinesis data analytics allows you to run analytical queries on the data stream in real time, which allows you to get a view into the source data and make sure aligns with what is expected from the data set. It is important to note that Amazon Kinesis is serverless service. Data analysis, speed layer. The focus on the analysis in this layer is to analyze the incoming streaming data in near real time and to react immediately based on the analyzed result within accepted levels of accuracy. This suggested architecture on AWS platform includes Amazon Kinesis data analytics for the speed layer. For the serving layer, we recommend using Spark streaming on an Amazon EMR cluster to consume data from Amazon Kinesis data streams from the speed layer. Visualization. In speed layer, Amazon Kinesis data analytics allows users to build custom analytical metrics that change based on real-time streaming data. Customers can use Kinesis data analytics to build near real-time dashboards uh, for metrics analyzed in streaming layer. Here you can see a speed layer. Data source is connected to Kinesis stream. It is connected to AWS Lambda. Kinesis stream and AWS Lambda is under stream processing, and AWS Lambda is connected to Kinesis Firehouse incremental stream. It is connected to real-time incremental view S3 bucket, and also Kinesis Firehouse is connected to Kinesis Analytics, and Kinesis Analytics is connected to visualization, and Kinesis stream also connected to Amazon EMR. Amazon, it is connected to merged view S3 bucket, and it is connected to visualization. As an example, we can consider Azure Stream Analytics. Azure Stream Analytics provides a managed stream processing service based on a particular running SQL queries that operate on unbounded streams. As another example, we can consider Storm and Spark streaming in an HD Insight cluster. Apache Storm is a distributed stream processing computation framework written predominantly in the Clojure programming language. Originally created by Nathan Mars and team at Backtype, the project was open sourced after being acquired by Twitter. It uses custom created spouts and bolts to define information sources and manipulations to allow batch, distributed processing, and processing of streaming data. The initial release was on 17th September 2011. Apache Spark is an open source unified analytics engine for large scale data processing. Spark provides an interface for programming entire clustered with implicit data parallelism and fault tolerance. Originally developed at the University of California, Berkeley's AMP lab, the Spark code base was later donated to the Apache Software Foundation, which has maintained it since. Now we are focusing on analytical data store. Many big data solutions prepare data for analysis and then serve the processed data in a structured format that can be queried using analytical tools. Here you can see analytics database. Raw data table is connected to derivative tables, and website events is connected to analytic database, and Maxpanel, Google AdWords, Salesforce, Facebook is connected to analytics database. Databases interact with analytic database. Analytical tools interacts with analytics database, and analytic database is connected to Salesforce. As an example, we can consider this. The analytical data store used to serve these queries can be a Kimball style relational data warehouse as seen in the most traditional business intelligence BI solutions. The Kimball approach to building the data warehouse starts with identifying the key business processes and the key business questions that users data warehouse needs to answer. The key sources, operational systems of data for the data warehouse are analyzed and documented. ETL software is used to bring the data from all the different sources and load into staging area. From here, the data is loaded into dimensional model. Here there comes the key difference. The model proposed by Kimball for data warehousing the dimensional model is not normalized. The fundamental concept of dimensional modeling is the star schema. The star schema, there is typically a fact table surrounded by many dimensions. The fact table has all the measures that are relevant to the subject area, and it also has the foreign keys from the different dimensions that surround the fact. The dimensions are denormalized completely so that the user can drill up and drill down without joining to another table. Multiple star schemes will be built to satisfy different reporting requirements. So how is integration achieved in the dimensional model? Here the Kimball proposes the concept of confirmed dimensions. The key dimensions like customer and product that are shared across the different facts will be built once and be used by all the facts. Kimball et al. 2013. This ensures that one thing or concept is used the same way across the facts. Another key artifact of Kimball model is enterprise bus metrics. This is the document where the different facts are listed vertically and confirmed dimensions are listed horizontally. Wherever the dimensions play a foreign key role in fact, it is marked in the document. This serves as an anchoring document showing how the star schemas are built and what is left to build the data warehouse. As an example, too, we can consider this. Alternatively, the data can be presented through a low latency NoSQL technology such as HBase or an interactive Hive database that provides a metadata abstraction over data files in the distributed data store. HBase is an open source non-relational distributed database modeled after Google's Bigtable and written in Java. It is developed as a part of Apache Software Foundation's Apache Hadoop project and run on top of HDFS Hadoop Distributed File System or Ingestion, providing Bigtable-like capabilities for Hadoop. That is, it provides a fault-tolerant way of storing large quantities of sparse data and a small amount of information caught within a large collection of empty or unimportant data, such as finding the 50 largest items in a group of 2 billion records or finding non-zero items presenting less than 0.1% of a huge collection. As an example 3, we can consider Azure Synapse Analytics provide a managed service for large-scale cloud-based data warehousing. Azure Synapse Analytics is a fully managed cloud data warehouse. As another example, we can consider this. HD Insight supports interactive Hive, HBase, and Spark SQL, which can also be used to serve data for analysis. Azure Insight is a big data relevant service that deploys Hortonworks Hadoop on Microsoft Azure and supports the creation of Hadoop clusters using Linux and Ubuntu. Now we are considering analytics and reporting. The goal of most big data solutions is to provide insights into data through analysis and reporting. As an example, we can consider this. To empower users to analyze the data, the architecture may include a data modeling layer such as a multidimensional OLAP cube or tabular data model in Azure Analysis Services. An OLAP cube is a multidimensional array of data. Online analytical processing OLAP is a computer-based technique of analyzing data to look for insights. The term cube here refers to a multidimensional dataset, which is also sometimes called a hypercube if the number of dimensions are greater than 3. In a tabular model, a physical relationship connects two tables through an equivalence over a single column. under certain conditions that we will be describing later, or in this moment, these additional descriptions are necessary. A relationship can define a constraint on the content of a table, even though such constraint is different from the foreign key constraint many SQL developers are used to. However, the purpose of a relationship in a tabular model is to transfer a filter while querying the model. As an example too, we can consider this. It might also support self-service BI using modeling and visualization technologies in Microsoft Power BI and Microsoft Excel. Power BI is an interactive data visualization software developed by Microsoft with primary focus on business intelligence. It is a part of Microsoft Power Platform. Microsoft Excel is a spreadsheet developed by Microsoft for Windows, macOS, Android, and iOS. It features calculation, graphing tools, pivot tables, and a macro programming language called Visual Basic for Application (VBA). It has been a very widely applied data spreadsheet for these platforms, especially since version 5 in 1993, and it has replaced Lotus 123 as the industry standard for spreadsheets. Excel forms part of Microsoft Office suite of software. As example 3, we can consider this. Analysis and reporting can also take the form of interactive data exploration by data scientists or data analysts. For these scenarios, many Azure services support analytical notebooks such as Jupyter, enabling these users to leverage their existing skills with Python or R. Project Jupyter is a project and community whose goal is to develop open source software, open standard and services for interactive computing across dozens of programming languages. It was spun off from IPython in 2014 by Fernando Pires and Brian Grenger. Project Jupyter name is a reference to the 3 core programming languages supported by Jupyter, which is Julia, Python, and R. And also a homage of Galileo's notebooks recording of the discovery of moons of Jupiter. Project Jupyter has developed and supported the interactive computing products Jupyter Notebook, Jupyter Hub, and Jupyter Lab. Jupyter is a NUM-focused, fiscally sponsored project. As example 4, we can consider this. For large-scale data exploration, you can use Microsoft R Server, either standalone or with Spark. Microsoft R Server, a machine learning server previously known as Microsoft R Server, is a flexible enterprise platform for analyzing data at scale, building intelligence apps, and discovering valuable insight across the business now with full support for Python and R. Transform your business with scalable enterprise-grade R and Python-based data analytics using your data and existing investments. Now we are focusing on orchestration. Most big data solutions consist of repeated data processing operations encapsulated in workflows that transform source data, move data between multiple sources and sinks, load the processed data into an analytical data store, or push the results straight to a report or dashboard. It selects and retrieves instructions from the main memory in proper sequence and interprets them so as to activate the other functional element of the system at the appropriate moment to perform their respective operations. Here you can see big data pipeline, and in big data space, we do see loads of use cases around developing big data pipelines. Typical data pipeline in big data involves few key states. All these states of data pipeline are waved together by a conductor of entire pipeline orchestra, OZ, etc. The conductor here is the central brain, which has all the rules and check what has happened. On the based on rules, it decides whom to call next. In some cases, stalls also allow you to configure what to do with the event. However, if we look closely at each stage in a big data pipeline, would be designed as a microservice, say ingestion microservice, data quality microservice, transformation microservice, etc. Most of the modern processing frameworks like Apache Spark, etc., are built with microservices architecture in mind. The cross-cutting concern of orchestration could be designed following microservices architectural patterns. So here you can see ingestion to data quality, there's a orchestration, and data quality to transformation, there's a orchestration. In joint transformation, enrichment transformation, custom transformation, and orchestration, and transformation to Hadoop is under orchestration. As an example, we can consider Azure Data Factory, a data integration service that allows creation of data-driven workflows in the cloud for orchestration and automating data movements and data transformation. Another example, we can consider Apache Uzi. To automate these workflows, you can use orchestration technology such as Apache Uzi. Apache Uzi is a server-based workflow scheduling system to manage Hadoop jobs. As another example, we can consider Squip. To automate these workflows, you can use an orchestration technology such as Squip. Squip is a command line interface application for transferring data between relational databases and Hadoop. This is the end of my presentation. Thank you very much for watching my presentation.